Hello everyone, I will be starting with the session now. Good afternoon, dear authors and invited guests. Welcome to Technical Session 6A. I am Dimahi Patel, the moderator of the session. On behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you to the 10th International Conference on Information and Communication Technology for Competitive Strategies, Jaipur, India. The 10th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in Jaipur, and the virtual event is being held through Zoom today and tomorrow, that is 16th and 17th December 2025. I hope you will enjoy the knowledgeable and interactive sessions through the day. In this session, we have 10 presentations. Each presenter will be given 10 minutes for presentation and 2 minutes for question and answers. On 9 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Before we start the session, I would like to introduce you all to the chair of the session. We have with us Professor Amar Buchade. Professor Amar is an associate professor at Vishwakarma Institute of Information Technology, Pune. He has over 18 years of teaching experience, and his primary research areas include distributed systems, cloud computing, distributed system security, computer networks, Internet of Things, and blockchain. A warm welcome to you, sir, and I invite you to kindly share a few words with us.
So, thank you very much for inviting me as a session chair. Right. So, all are requested to present it within a deadline. So, wish you best luck. Thank you very much.
Yes, thank you very much, sir. We will be starting with the presentations now. I would like to call Pradyumna Ramgirwar to present his study on 10 Gbps ROF transmission model at 60 GSZ using NRZ for 5G networks. Pradyumna sir? Or any of the co-authors present with us? Alright, I will be calling the next one. Prutha Annadate. Prutha ma'am, are you present with us?
Yes, we're here. Can you hear me clearly?
Yes, ma'am. Please present your study on deep learning in neuroimaging, advanced CNN models of brain tumor detection and classification.
Thank you very much. So, a very good afternoon to one and all present today. My name is Prathan Natate, and I'm here with my teammates, Rugved and our mentor, Dr. Murar Annadate. The idea of today's session is to present a topic on deep learning in neuroimaging, talking about the model that we have established, which is doing both classification and detection. Can we move to the next page, please? So, all of us know that brain tumor diagnosis is not just a classification problem, it's a fundamental and time critical decision. Manual MRI interpretation struggles with large scale volume and complexity. So, our contribution is a unified CNN framework that performs both tumor detection and classification. And we are intentionally using a sequential CNN for detection and a fine tuned VGG16 for classification. Now, this choice prioritizes deployability, computational efficiency, and reproducibility, which are all critical for real world clinical settings. Before we begin, I would like to point out that we have achieved 99% detection accuracy and 98% classification accuracy, demonstrating precision and reliability. Now, this framework supports faster diagnosis and reduces radiologist workload. Let's move on to the next page. We'll talk about the need of this study. As you can see on the table in the right, recent medical news have consistently highlighted a growing gap between imaging capability and diagnostic efficiency. Even with high resolution MRIs, subtle tumors are missed and misclassified due to manual analysis mostly. So, this is where our research comes into the picture. We can make clinical workflows much faster without compromising diagnostic confidence. Of course, all of this is just a amplification to human aid and not actually a replacement. Let's move on to the next page, please. So Rugved will continue with some more details about methodology. Over to you, Rugved.
Thank you. Talking about the dataset preparation first. So for our study, we utilized two comprehensive data sets. The first is the brain tumor MRI dataset containing 1,311 images, and the second is BR35H brain tumor dataset with 3,000 images. All the links are provided in the references. So we've split the data with 89.5% allocated for training and the remainder for testing. So moving on, let's talk about the different classes of the tumors we have identified. So our classification focuses on three distinct brain tumor types based on their anatomical locations. Gliomas are typically located within the brain tissue itself, often deep inside the cerebral hemispheres. Meningiomas are found outside the brain tissue, arising along the brain's protective coverings and commonly occurring near the skull. Pituitary tumors are located at the base of the brain. Sorry. Pituitary tumors are located at the base of the brain within the pituitary gland, close to the critical structures as the optic nerves. Additionally, MRI images without tumors were included during detection training to help the model accurately distinguish between healthy tumors and tumorous brain tissue. MRI views. So our in the MRI views, the dataset incorporates multiple views to provide comprehensive spatial information. These include the axial view from the top, sagittal view from the side, and coronal view from the back of the brain. So talking about how we pre-process the data, our pre-processing pipeline involves several critical steps. First, we converted all images to a standardized 200 by 200 resolution in grayscale. We then applied blurring techniques to reduce noise, followed by thresholding and erosion operations. Finally, we employed contour detection to crop each image to the region of interest, ensuring our models focus specifically on the relevant brain structures, as you can see here. And then talking about the detection model architecture, for tumor detection, we developed a sequential CNN that achieved an impressive 99% accuracy. Our architecture employs a systematic approach with multiple convolutional layers that extract features from MRI images. Each layer is followed by max pooling operations to reduce spatial dimensions while retaining the most important features. The sequential nature of our CNN allows it to learn hierarchical representations, starting from basic edges and textures in the initial layers, progressing to more complex patterns that are characteristic of brain tumors in the deeper layers. This architecture was specifically designed to balance model complexity with computational efficiency, making it suitable for practical deployments in clinical settings. Talking about the classification architecture, we leveraged transfer learning using a modified VGG16, which achieved a 98% accuracy. VGG16 is a well-established deep learning architecture originally trained on millions of natural images. We adapted the pre-trained model for our medical imaging task by fine-tuning its parameters specifically for brain tumor classification. The key advantage of using transfer learning is that it allows us to achieve high accuracy even with limited medical data, which is often a challenge in healthcare applications. The pre-trained weights from VGG16 provide a strong foundation for feature extraction, which we then customized for a specific classification task. We modified the final layers of VGG16 to output the predictions for our three tumor categories, and through careful fine-tuning, achieved performance it distinguishes between the three types of tumors. Now, Prutha can continue the findings for our study. Thank you.
Okay, thanks, Rugved. Now I'll talk about what we actually achieved out of the study. First of all, detection is the gatekeeping task. If detection fails, then classification becomes irrelevant. So it was relevant that we first had the detection model be very accurate. So very confidently, we have achieved 99.43 training accuracy and a 99% validation accuracy. More importantly, the model shows stable conversions with low training and validation loss. Now, conversions, for those who don't know, indicates that the model has learned meaningful tumor features rather than just memorizing noise. And compared to existing models, as you can see in the table on the right, we have on the same data set, our approach achieves significantly lower loss and hence actually manages accurate tumor localization. Now let's talk about the findings for classification. Next page, please. If you can see now, the output on the right is the actual output from our model. Once your tumor has been detected, accurate classification directly impacts what treatment you can give to the patient. So our fine-tuned VGG16, as explained by Rugved, after careful fine tuning for the final layers, achieved 98% classification accuracy, which farly outperforms existing models. Notably, convergence was achieved within approximately 10 to 12 epochs. Again, early convergence reflects effective transfer learning and reduces the risk of overfitting. Now, the model has successfully discriminated between gliomas, meningliomas, pituitary tumors, and also tumor brains. That was classified in your detection algorithm. Let's move on to the next point, which is the discussion. So, we have now clearly established that CNN based systems significantly improve diagnostic accuracy while reducing analysis time. We deliberately avoided designing a complex custom architecture, which could have been done because lightweighted models and fine tuned models are easier to validate, reproduce, and deploy, which is very important in settings where MRI analysis is hard to do and it's not very much available in small localities. Let's move on to the next page. The importance and future work. Of course, early and accurate tumor detection, which again links back to the need for this study, plays a very critical role in improving patient outcomes. As we saw on slide 2, nearly 42% of gliomas are not actually detected on time. So, this framework is suitable for telemedicine and low resource healthcare settings and also supports medical education. So, future work can focus on actually deploying this in medical settings and fine tuning wherever required. And this will actually help cross institutional dataset validation as well. Let's move on to the last slide now. Yes, so thank you very much for everyone present today. And we hope that what we have presented is not just research that is theoretical, but also practical research which can be used and implemented in real life settings. So the floor is now open to questions. So if anyone has any questions,
From
please
where
feel
you
free to
have
ask.
picked up the database, dataset?
Sir, the data set is open source. Prugvet, could you go back to the slide, please? So we have two distinct data sets that we have combined. All together, they come around to 4,000 images. Both of them are open source, available on UCI Machine Learning Repository and Kaggle both.
How many layers of CNN you have taken then?
There were 6 CNN layers, sir.
Why 6? Why?
Because so we as I mentioned, we did multiple iterations of it, and 6 is where we found the best validation accuracy, because training accuracy is easy to achieve, validation accuracy also needs to be high.
Okay. Okay. Thank you very much.
Thank you, sir. Is if anyone else has any questions? Okay.
All right. Thank you very much, ma'am.
Thank you so much.
Now, next, I would like to call Koteshwara Rao Malaparapu sir to present his study on development of a smart dental chair system with real-time postural adjustment.
Good afternoon, ma'am.
Good afternoon, sir.
Ma'am, my screen is visible.
Not yet, sir.
My screen is visible.
No, sir.
No. Now is working, ma'am.
Yes, sir. We can see your ICTCS folder.
In PPT.
Please open PPT.
I already working, sir. Okay.
But it is not visible.
Now is working, ma'am.
Please give me a minute to check, sir.
Okay.
No, sir. Still only your ICTCS folder is visible to us.
Now, ma'am?
Yes.
Yes, sir.
Please,
Please
Okay.
start the presentation.
Thank you. Thank you.
please make the video on also.
Good morning, good afternoon, everyone. This is Kodeswar Rao. I'm working as a research scholar in the Department of ECE, SRM University, AP. This work is under the guidance of Dr. K.A. Sunita, HOD and Associate Professor in Department of ECE. Our title is A Development of Smart Dental Chair System with a Real-Time Postural Adjustment. So these are the Koada, Madhuri, Divya, Sai Praveen and Kiran sir. So my contents are the abstract, introduction, block diagram, functional prototype, working video, and conclusion. So in this paper, present a novel real-time postural correction system designed especially for the dental practitioner. So during the dental practitioner, when patient is coming, they have doing the experiment, they have bent beyond the limits. So in this problem, you identify the ultrasonic sensors will be give the immediate feedback. So the system will be forward leading a postural and provides the instant warnings. A visual feedback through a Arduino Mega and LCD display. This system helps to reduce the long-term back and the neck problems was successfully tested at the Sebar Institute of Dental Sciences in Guntur. So there the slides shows the approximately 60 to 80% of the dentistry suffers from the neck or back pain for every year. During the dental procedure, the dentist often bend forward unknowing for a long duration. So the existing solutions mainly focusing on the chair design, wearable devices, but they are not doing the provide the real-time posture feedback. So this gap is motivated to develop a smart real-time postural monitoring system. So these are the literature survey. These tables will be compare the existing of the postural correction methods such as a variable, a smart arguments and erroneous shades. Although the effective of the system are often expensive, insect and uncomfortable for the dentist. So none of them provide a simple chair mountain, a real-time feedback system, especially for the dental practice. So the figure will be show the how the dentist will be doing the difference between the good and bad posture correction. The dentistry unwinding bend forward the long period. So the unwinding during the long period, so leading to a musculoskeletal disorders, the pure posture. So affect the dentistry comfort treatment efficiently. So even the patient is a comfort. So based on this one, we will identify the objectives. So the main exploration, the objective of a project is to develop a real-time posture monitoring system to provide the instant feedback like so when doing the dentistry they will give a feedback like a good, bad and very bad position to design a non-invasive and cost-effective solution to ensure the easy of integration without modifying the existing model chairs. So to build the habitual procedure awareness among the dentistry. So what is the novelty? So our novelty, our system is the first real-time chair mounted posture monitoring solution designed exclusively for the dentistry. So what are the make our system is a unique, a non-invasive, a dentist specific, a real-time feedback and no chair modification. So what are the previously existing chair will be always use the chair will be a small modification. So this is the system how the system work and implementation, the problem understanding and component selection, system design, design collaboration, and programming and simulation. So this is the general block diagram. We are using the block diagram for the um, real-time postal dental chair. So they are placed with three types of sensors, and they're connected to Atmega 2560 microcontroller. Finally, give the LCD display. So here the block diagram shows the ultrasonic sensors mounted on the dental chair. Continuously it will measure the distance between the dentistry and the chair. So the Arduino Mega, it will process the data display posture status on the LCD screen. So this enables the real-time posture correction. So why use the ultrasonic sensor? So we use the ultrasonic sensor because they are provide a non-contact accuracy and reliable and distance measurement. So the Atmega 2560 microcontroller was chosen for it for high processing power, multiple input output pins, and real-time performance, making it is ideal for the application. So this is the flow chart. The flow chart will start with the start and LCD display initiating. After the serial output, how the good position or bad position or very bad will be show the this image show the final working. Next one, this is the functional prototypes. Here the three ultrasonic sensors replaced top, middle, and bottom. So these are three ultrasonic sensor will be connected with the finally product prototype. Here LCD display will be show the how the system will be working. The dentistry bend is toward or to forward will be show the good, bad, or above. So we will in this next slide will be show the how the system will be working, the working model of the system.
Device designed specifically for dentists. With three ultrasonic sensors strategically placed on a chair, the system effectively tracks posture changes during dental procedures. When the dentist sits upright, the display shows good pose. If the dentist leans slightly forward, it alerts with a bad pose message. Bending further triggers a critical warning with dangerous pose. This solution aims to prevent excessive bending, promoting better posture and reducing strain on dentists. A simple yet impactful innovation for healthier practice habits.
When the dentist bending more will be show the dangerous position. So, or the conclusion is, in conclusion, our system provides a simple, affordable, and a effective solution for the posture correction in the dentistry. It improves the health and reduce the long-term pain and enhance the quality of the patient care without alternate edges in the dental setup. So this makes it a practical, real-world solution. So in future plan, the audio alert hands to your portrait generation. They implement the data logging using the SD cards. They store the portrait regarding this one. So upgrade the wireless and battery power. We have integrated the machine learning to reduce the false alert for the feedback. Introducing the cloud storage for the more remote access and database. Thank you for your time and patience. I will be happy to answer any questions.
Any accuracy you have received got from this?
Actually, the system is developed in SRM AP and will be tested in the Seba Dental Institute, Seba Dental College. They feel very very happy. So in the accuracy nearly 90%, we did not perform any the machine learning algorithms like that. So when we are testing the 13 doctors, they have feel very happy. So in the scenario, you have also received the patent. Patent filing is completed, and you receive the patent, and also you receive the second prize for the Dental Chair Association in the New Delhi.
Which machine learning algorithm?
No machine learning algorithm we are used, sir, just implemented, and by using the some basic codes for the Atmega controller, we are using code. No machine learning algorithms, sir.
Okay. Thank you very much. Thank you. Okay.
Yes, thank you, sir, for your presentation.
Thank you, ma'am.
Now, next, I would like to call Mohammad Azharuddin Adhoni. to present his study on end-to-end connectivity and throughput testing in a virtual 5G network using Open 5GS and URAN-SIM.
Uh, Good afternoon, ma'am. Is my screen visible?
Not yet, sir. Can you please confirm if you are Mohammad Azharuddin Adhoni?
Yes, ma'am.
Okay.
Ma'am, now is my screen visible?
Not yet, sir. Sir, please try to share the presentation or the whole screen if possible.
Ma'am, I'm trying to share, ma'am. Ma'am, now at least the file explorer page is open to you. Hello, ma'am.
Yes, sir. Yes, sir. We can see the Explorer page.
The PPT, ma'am.
Mm, no, sir. Not the PPT yet.
Ma'am, my friend is also there in the meeting. He said it is visible, ma'am.
Yes, sir. It is visible to us now. We can see your
But make it full
starting
screen.
screen.
Yes, sir. Yes, ma'am. Now it is like visible, ma'am, right?
Yes, yes, sir.
Okay, ma'am. Good afternoon, everyone, and my fellow researchers. Today, I'll be presenting a work titled on end-to-end connectivity and testing in a virtual 5G network using Open 5GS and UV ransom. So, in this presentation, we'll be like mostly focusing on what we implemented and like how we tried to verify it and what are the results that we achieve. So, speaking 5G networks they like promises us on the high data rates, ultra low latency and reliable connectivity. However, like understanding how these compromises are achieved internally requires like hands-on experimentation with real 5G protocols. So in this work, basically we built a complete virtual 5G environment using open source tools to study real control plane and user plane behavior, like instead of relying like totally on the theoretical models. So the motivation behind our project was basically gaining practical exposure to the real 5G core and RAN signaling, and basically to create a low cost reproducible 5G testbed suitable for academic research and performance evaluation. And the core objectives that involved in the project were basically to deploy a functional 5G core using Open 5GS, and to integrate a simulated G-Node B and user equipment using UV ransom, and to verify end-to-end connectivity using protocol analysis for performance testing, and to evaluate throughput, latency, jitter, and retransmission. So in the system overview, as you can see, so we have implemented basically a complete end-to-end 5G network in a virtual environment. So Open 5GS was used like for the 5G network, providing the AMF, SMF, and other functions. And UV ransom was basically for the simulation of the radio access network, including G-Node B and the user equipment. So all the components were firstly deployed onto the Ubuntu 2024 22.04 using a VMware Workstation Pro. And why we chose basically like Open 5GS was basically it gives us the closely follow-ups for 3GPP standards and allows real control and user plane testing. And UV ransom provides accurate simulation of G-Node B and user behavior using real 5G protocols. Like together, they allow us to study realistic 5G signaling without specialized hardware. So firstly, we started by installing and configuring the Open5GS. Later on, we have used MongoDB for storing the subscriber information. And Node.js was like installed to enable the Open5GS web UI. Like after building the Open5GS, we tried to verify that all the core services such as AMF, SMF, and UPF like were running correctly. And we also tried to verify it by the Oxten interface that was enabled. Like basically, it enables the user plane tunneling between UE and the core. And using the Open5GS web UI, we added subscriber details. We After using the Open 5GS web UI, we added the subscriber with IMSI, authentication keys, and slicing parameters. This step was essential to enable successful user equipment authentication and PDO session establishment. And later on was the setuping of the RAN implementation, basically of the UE ransom. So we tried to build the UE ransom, and which was basically compiled from the GCC and G++ compilers, and we configured the custom gnode B and the UEML files. The gnode B was configured with SCTP and NGAP IP addresses and EMF connection parameters. And when the GNB was started, the SCTP and NGAP setup was successfully established. And why we chose the Wireshark was to check the heartbeat connection between the Gnode B and the core network also. And so Wireshark was basically used for the also for the to verify protocol correctness. We captured the stream control transmission protocol traffic between the Gnode B stations and AMF. As you can see here, we have captured the SCTP init and init acknowledgement, and also the ng-gap setup request and response. So this basically confirmed as the stability of the control plane activity that we have performed for the connectivity. Later on was the UE registration and authentication, wherein UE authentication was aligned with the subscriber data. When the UE was executed with root privileges, authentication succeeded and tunneling interface was created. And Wireshark captures confirmed the RRC connection setup, also the security mode command, and the registration acceptance. So we performed various tests to get the connectivity that was developed. So we performed the ping test to basically verify the connectivity from the user to the base station, that is Gnode B, and also from UE to the core 5G core through Oxten interface. So after the successful ping response that was confirmed, the user plane routing and tunneling was being confirmed. And the performance evaluation, like basically main focus was on the Hyper-3 test. So in the test part, we had done for two separate. That was one was the TCP part and the UDP part. So in TCP results, we got to know that from UE to GNB, throughput was approximately 6.1 Gbps, and UE2 core throughput around 5.7 Gbps was achieved. And in UDP tests, the we simulated the real-time traffic that was helpful for applications such as video or gaming. Here bandwidth we had set up a constant of 100 Mbps, and jitter we got to know that it was zero point 0.1 milliseconds. So key observations that I can say is we got a stable SCTP and NGAP signaling, which gave us an confirmation for the correct control plane operations, and we received a high TCP throughput that demonstrated efficient data plane setup and a very low UDP jitter. So it confirms the suitability for real-time applications. And so basically, to conclude, we successfully implemented and validated and end-to-end network using Open5GS and UE ransom. We verified real 5G signaling and achieved a high throughput with low latency in a virtual environment. So this project gave us a strong experimental foundation for the advanced 5G research paper. So that's all.
You have utilized for this purpose.
Yes, sir.
Bandwidth.
Yes, sir. Bandwidth we had kept 100 Mbps.
And what latency jitter you observed through this?
Yes, sir. Jitter we got around 0.1 milliseconds, sir. And there was no retransmission for the UDP tests.
Okay. Okay, good, good, good. Thank you.
Yes. Okay, okay. Thank you so much, sir.
Yes, thank you, sir. Next up is by the same author, Mohammad Azharuddin Adoni, to present his study on network slicing using Open 5GS and URAN-SIM.
Is my PPT available, ma'am?
Yes, sir.
So, good afternoon, everyone. My name is Narayan. I am the co-author of this paper. So today we are presenting our paper titled Network Slicing using Open 5GS and vRansom. This project focuses on how a single 5G network can support different types of services like high-speed internet, ultra low latency, and IoT devices at the same time.
Narayan, sir, just to confirm, will you be presenting this paper?
Yes, ma'am.
Just to confirm, will you be the one to present this paper?
Yes, ma'am. I am the only one
Okay,
presenting this.
okay. Please continue.
So in current 5G networks, users and applications have very different requirements. Some applications need high data rates, some need extreme low delay, and others need only small data occasionally. The problem is that the static network slicing does not adapt when network behavior changes. Once a user is assigned to a slice, it stays there even if the requirements changes. This leads to poor resource utilization and reduced quality of services. Network slicing is one of the key features of the 5G core. It allows a single physical network to be divided into multiple logical networks called as slices. Each slice is designed for a specific type of a service. In our project, we built a fully 5G core network using Open5GS and UV ransom to simulate our devices and base station. The system continuously monitors traffic and dynamically assigns users to the most suitable case. So why there is a need of network slicing? Without slicing, all the traffic is treated equally. This causes delay-sensitive applications to suffer when the network is congested. Network slicing solves this by isolating traffic and prioritizing resources based on the service needs. We work on three standard 5G slices types. The first is EMBB, Enhanced Mobile Broadband. This slice is optimized for high data rates and is used for applications like video streaming and high-speed internet. The second one is URLLC, Ultra Reliable Low Latency. This slice focuses on extreme low latency and high reliability, suitable for critical applications like autonomous vehicles and robotic surgery. Then the third is MMTC, Massive Machine Type Communication. This slice supports large number of low power devices like sensors and IoT nodes. The objective is to implement a 5G core network with multiple slices using Open5GS and to simulate user equipment with traffic patterns using UV ransom. The tools we and technologies we use are the first one is Open5GS. So Open5GS is an open source implementation for 5G core network. This follows a 3GPP standards, which means it behaves like a real telecom 5G core. The second is a UV ransom. UV ransom is to simulate both user equipment like mobile phone and base station. Instead of using real hardware, we simulate everything in a software, which makes testing easier and cheaper. The third is Open5GS Web UI. This is a web-based dashboard that lets us see which users are connected, which slice they are using, and whether the sessions are active. We ran everything on Ubuntu Linux because networking tools work best are stable on Linux. These are the some files we have configured. The first one is UV YML file. This UV configuration file defines the identity of a user equipment. It includes the IMSI, which is a international mobile subscriber identity, which is the unique subscriber identity and security keys used for authentication. It also specifies the SST slice service type, which tells the network which slice the UV should request. The another one is GNB file. So GNB configuration file defines the 5G base station parameter. It includes the PLMN, which stands for Public Land Mobile Network. It is a combination of MCC, Mobile Country Code, and MNC, Mobile Network Code, used to identify mobile network. It also defines the tracking area code Tracking area code is used by network to manage UV mobility and locating trafficking. The file contains IP addresses which defines how GNB communicates with core network. It also lists the supported slices and GNB knows which slice request it can accept. The third is AMF. So AMF is a authentication access and management function. This configuration file controls user registration and mobility management. It defines PLMN supported by the network so that only valid UVs can register to the network. It also specifies supported SSTs, which tells AMF which network slices are allowed. The web UI is a database entry. The web UI is used to add subscriber information into the system database. Here we define the IMSI authentication keys and allowed slides information for each UV. So this is our block diagram. The process starts with UV and GNB simulating using UV ransom, which generates traffic via tools like iPerf and Ping. The live traffic monitoring module continuously monitors the latency and throughput and detects the UV's service in real time. Based on this, the dynamic slice switching Uh, one second. This based on this dynamic slice switching logic selects the appropriate slice. The SST1 is for EMBB, SST2 is for URLLC, and SST3 is for MMTC. The Open 5G core network enforces this by rerouting the traffic through the corresponding slice. So our methodology is first we set up a 5G core network using Open 5Gs. We configure the components like AMF, SMF, UPF, and WebUI. Then we created the three network slices. We basically created three files and named them EMBB, URLLC, and MMTC. And after that, we performed UV simulation and UV ransom. Multiple user equipments were simulated and connected to the core network. Each UV was mapped to a slice either based on predefined configuration on or its traffic behavior. After that, we implemented dynamic slicing logic. This system monitors traffic in real time and checks parameters like throughput demand and latency sensitivity. Based on this, UV are dynamically reassigned to the most suitable slice. Then we carried over traffic generation. We used UDP traffic to measure throughput and packet loss. Each slice was tested using controlled and slice-specific traffic patterns. Finally, performed metrics and collected analysis. We collected throughput, latency, and packet loss values. This data was logged and analyzed to evaluate slice performance and verify proper QoS handling. So as you can see in the results, the graph shows the throughput achieved by each. So the blue line says the EMBB. EMBB had the highest throughput, which is around 80 Mbps, and uh, that orange line describes URLLC, which has around 20 Mbps, and MMTC has around 1 Mbps, suitable for IoT sensors. And the packet loss was high for MMTC because it has very low throughput. So your URLLC has 0% packet loss because it has a high because it has low delay. And another one is MMTC. Yes, sorry, MMB, which has very low loss, which was around 0.45%, and the MMTC had around 0.2 to 0.9%. So latency was lowest for URLC, which describes its standards. So it was around 1.5 ms, and for AMBB it was around 10 to 30 milliseconds, and for MMTC it has around 30 to 90 ms. So URLC strictly meets its latency demands. So 1.5 milliseconds is really used for autonomous vehicles and robotic surgeries where the delay is critical. So this was the average throughput, latency, and MMS packet loss. So EMBB has the highest throughput, and URLC is second to it, and MMTC is next to it. So and for latency, URLC has the lowest delay, and packet loss, MMT has the highest packet loss. So in conclusion, we would say that our project successfully demonstrated how network slicing can be implemented and tested in 5G core network using Open5Gs and UV ransom. We created 3 slices for EMBB, URLNC, and MMTC and showed that each slice behaves according to its requirements by monitoring traffic and dynamically assigning user to the appropriate slices. Thank you, and we are open to your questions.
What accuracy you have achieved?
So, accuracy, our project is not about accuracy. We are are mirroring the network slices. So, as you can see in the result, our EMBB has the accordingly, because EMBB needs highest throughput, and we achieved accordingly. We achieved 80 to 85 Mbps throughput, and same as for URLC and MMTC. So URLC needs to be very low delay. So we achieved around 0. Um, we achieved around 1.5 milliseconds. So
Okay. Good work. Thank you very much.
thank you, sir.
Yes, thank you, sir, for your presentation.
Can I present, ma'am?
Yes, ma'am.
Speech, ma'am. On speech, it is Trupti Kulkarni.
Do you have any other emergency, ma'am?
Yes, actually, now my internet is not working properly. It is getting disconnected in middle.
All right, sure. Please give me a minute.
Okay.
Yes, Tripti ma'am, please present your paper on speech detection of pathological voice disorders non-invasively using machine learning algorithms.
Yes, ma'am. Yes. Yeah, good afternoon, all of you. I'm Dr. Trupti Kulkarni, presenting a paper on speech detection. One second. Speech detection for pathological voice disorders non-invasively using machine learning algorithms. Actually, we are 5 of us, myself, Dr. Vasudeva sir, Renuka Prasad, Rupa K.R., Sri Vidya, and Mandar Jatkar. We are the authors of this paper. So the flow goes in this way. I'll just introduce the topic. It's like finding the diseases related to the voice using the machine learning languages. We use the voice related data sets, and we could find out we use certain parameters, and then we could find out the whether the person is deceased or not deceased, and which algorithm is suitable from the algorithms we have used. So voice disorders, voice is a speech is very, very important factor in our health regarding to the health concerns, especially for in the teaching profession. We are communicating every day, and because of the pollution around us, biological factors, and the communication we are doing nowadays, and the food we are eating, through because of all these things, voice disorders is a major factor which we usually neglect. So early detection of this and non-invasively was our main concern, where we use the machine learning language, and we continued with our project. So the methodology we used is voice to the data sets. We did the pre-emphasis of that. Framing and windowing was done. FFT was done. Then null filter bank was used. Logarithms was passed there. DCT was done, and MFCC features were used to extract the whole process. So random forest, this is the methodology I'm talking about. Random forest algorithms, flowchart I have put over here. We design by choosing the parameters. We are using bootstrap method to extract the training samples with the replacement. Train a decision tree. Now, and then I take a decision by choosing the parameters, number of decisions, 3 less than given value. If yes, go back again. If no, go further, vote or take the arithmetic average to get the result, and then finish the algorithm. Second one used is logistic regression algorithm. Initialize the data set, pre-processing is been done, feature selection, applying the algorithm, and then performance measurements are being taken. So this is the results part after passing through both the machine learning algorithms. Each machine learning algorithms output is been taken. So table 1 consists of the performance of different features for the stage 1 classification of the particular subject. So total number of samples taken here is 110 healthy samples, 36 unhealthy, total 110 samples. In that 36 healthy samples and unhealthy were 74. And the disease identified was hypokinetic dysophenia, hyperkinetic, and reflex laryngitis. Correctly classified were 65 for hypo, and wrongly classified are 99, accuracy 77. For hyperkinetic, correctly classified is 34, wrongly classified is 11, accuracy was 75. Reflex laryngitis is 39, correctly classified, wrongly classified is 12, accuracy is 76. In the same way, for logistic regression also, it has been done. And this is the output of that, 110 samples, 48 healthy, unhealthy 62. So same disease, again, hypokinetic, correctly classified 47, wrongly 14, accuracy 77. Hyperkinetic 51, wrongly classified 15, 77 is the accuracy. Reflex laryngitis was 24, correctly classified, 17 wrongly classified, 77 is the accuracy. So when we compare both the tables, both the methods, we come out with the result of comparison of both the methods. Total samples 110, random forest accuracy 75%, logistic regression accuracy 77%. Random forest correctly classified 34, wrongly classified 11, accuracy 75. Logistic regression 51 correctly classified, wrongly classified 15, accuracy is 77. So with this, the final results we achieved were random forest classifier is demonstrated as a superior performance across all the metrics, which achieved an accuracy of 91.368%, indicating that approximately 91% of all voice samples were correctly classified. Its precision of 90.57% shows that nearly 91% of the samples predicted as pathological were correctly identified, while the recall of 92.13 reflects the model's ability to detect more than 92% of actual pathological cases. F1 score of 92.0 confirms a strong balance between precision and recall, highlighting the model's overall reliability. In comparison, the SVM classifier achieved slightly lower performance with an accuracy of 89.79, precision of 88.29, recall of 90.26, F1 score of 89.26. So conclusion I would like to give is, in machine learning methods provide well-defined view of accuracy, precision, sensitivity, capacity of differentiating the voice disorders using various databases. Our result consists of different sets of voice samples needed in the identification process. SVD is used that demonstrated to us the logistic regression was better compared to random forest by a thin margin in the accuracy. Our result turns out that by allowing the use of continuous speech instead of a single vowel, it can lead to improved results in the diagnosing process, as it provides a rich information in the voice disorders diagnosis. These are the references which we are used in the literature survey to continue with the paper by studying the all different papers. There are still many more references, but I have selected few and added over. Thank you.
Yes, so please see, accuracy somewhat is less. What is the reason?
Sir?
Accuracy you
Accuracy.
mentioned is somewhat less.
Yes.
What is the reason?
Yes, sir, because when we used this machine learning algorithms, it's almost 1 year back, the project was being done, sir. So at that time, we got with this results, and later, again, we are improvising with this particular data, sir. The next version we are doing with that, sir. and we'll be going with the
That
next
is
work
right.
and the
But
paper.
can you please justify this? Why the accuracy is less now?
So, yes, sir, when we took these algorithms, sir, and we performed the machine learning algorithms on the data set, we got this particular accuracy at that time, sir.
That is right.
Yes,
Why
sir.
you got less accuracy? That is my question actually. Any lack in the implementation of algorithm?
Yes, sir, we tried with many algorithms, and actually that time we didn't have much time to compare with some more algorithms or recheck our accuracy. But since even we know that the accuracy was lesser, we are working on it now, sir.
So as a technical person, you should give the proper justification,
Yes, sir.
explanation for this. Okay.
Yes, sir. Yes, sir.
The job has been done by algorithm, right? But you
Yes, sir.
should know the internal details, okay? Why it is less. In order to increase it, what can be the modification in the algorithm that you can decide. Okay.
Yes,
Thank you
sir.
very much.
Yes. Thank you, sir. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Now, next, I would like to call Saurabh Sagar to present his study on precision agriculture, combining agro-meteorological, farm level, and remote sensing data to predict regional yields.
Excuse me, ma'am.
Yes, sir.
Ma'am, sorry to interrupt you, ma'am. Actually, I was like in the fourth number. So my paper title was End-to-End Connectivity and Throughput Testing in a Virtual 5G Network using OpenFiGS and URNC, ma'am. During that, while I was presenting the paper, I got the share screen issue, right? So you had told me like who was presenting the paper. So Mohammad Azuruddin was actually our like guide and professor, ma'am, in our college. But Ilyas Kinal has presented the paper, ma'am. Just for the clarification, I had asked you. Like I told you, ma'am.
Okay, sir. Okay. So you are the co-authors of the paper. Am
Yeah,
I correct?
yeah. Ilyas Kinal, I have presented the paper, ma'am, and Mohammad Azuruddin is just our professor. So like this might have been a miscommunication between you and me, ma'am. So just for the
Okay.
clarification.
Yes. Thank you so much for clarifying it, sir.
Okay,
Don't
ma'am.
worry. Yes. Thank you.
Okay, thank you.
Saurabh Sagar, sir. Can you hear me? I repeat, Saurabh Sagar. I believe, sir, your mic is muted.
1 minute, madam. The mic is unmute. Okay, now it is hearing now.
Yes, sir. Yes, sir. We can hear you now. Please share your screen and start with the presentation.
Okay, madam. Screen visible, madam, now?
Yes, sir.
Okay. Okay, good afternoon, everyone. My topic is precision agriculture combining agro-meteorological, farm level, and remote sensing data to predict regional yields. My name is Saurabh Sagar and co-author is Mahantesh N. Bisde. Introduction. With respect to title, climate means what is the need of this work? It means the World Health Organization has predicted that every 2,50,000 extra deaths per year by 2030. So due to because of food security risk. So agriculture depends mainly on the weather and contributes to emissions. So precision agriculture improves yield and saves resources. Global example means many countries are using different softwares to monitor the crops and all. So technical like sensors, drones, GPS, AI and ML enables better decisions. Accurate yield prediction reduces risk and waste. So growing of AI plus remote sensing boosts prediction accuracy. So we used about deep learning and machine learning techniques. Deep learning handles the CNN, RNNs and LSTMs. BNNs capture complex crop patterns. CNN and CNN LSTM improve satellite-based yield prediction. LSTMs excel in weather and soil forecasting. Machine learning effective for non-linear crop data. And BPNN plus independent RNN enhances yield estimation tools include PyTorch, CNTK, and MetConverse and SkySettler. Data scarcity handled by augmentation, weak, super, and domain adaptation. These are the means use these algorithms are used to predict the yield. Next, remote sensing techniques are a reliable low-cost method for timely crop and surface monitoring. Uses satellites, drones, and photogrammetry, multispectral and hyperspectral sensors. Fluorescent signals detect plant stress and nutrient deficiency. Stress means there are two types of stress: biotic and abiotic. Biotic is caused by living organisms, and abiotic is caused by external resources. So, what are the key vegetation indices? Is NDVI, AIVI, PRI. So, these indicates the vegetative indices and the photosynthetic efficiency. So, that indicates the disease. So, these are some of the literature survey part related to our area: precision agriculture, climate relevant agromethodology, integrated agriculture forecasting, and all. Crop model and policy, precision farming and water security, maize monitoring. There are different means the yield prediction is used for different crops and different regions and all. So we found out from this literature survey that most studies use only single type of data. So we are using here three types of data. Okay, the integrated model we are using. So that is combined of weather, farm practices, and crop health is often ignored. Integrated models using all data sources are limited at the regional level. So comparison between single source and integrated models is insufficient. So there is need for simple and accurate integrated model for better yield prediction. Accurate yield prediction is crucial for farm planning and also once we get the what is the yield. So if the yield is decreasing, so what is the reason and all we can find it out and we can change the path to the destination. So research objective is like to predict the regional crop accurately by integrating agrometeorological, farm level, and remote sensing data to compare performance with single source and integrated models using RMSE, root mean square error, mean average percentage, and determinant of coefficient. So identify most influential factors affect crop yield with emphasis on rainfall, NDVI, soil mass, and that's all. Methodology we use this quantitative and data-driven approach to predict regional yield crop productivity. Use this data sets from agrometeorological data. We use temperature, humidity, and rainfall. In farm level data, we took the sowing irrigation inputs. Remote sensing data are Sentinel-2 and Landsat-8. Soil moisture vegetation indices are taken. Data pre-processing is normal cleaning, pre-processing with the crop roll calendar. Modeling techniques used are regression, random forest, gradient boosting, and deep learning models. Evaluation metrics are IC, MAE, MAP, and R square. Next, we got the results like this. The first one is means if we use only agrometrical data only, then we got the R square value as 0.68. So if we only use farm level model, then we got the 0.72. And for remote sensing, we got 0.0. So by combining all these, we found out that new model is integrated model, agrometrical first plus remote sensing. So by combining all these three, we are getting better performance, that is 0.89. So this is a graph of actual versus predicted yields. Predicted yields closely match actual yields across region A to A. Minor deviations that can be ignored. Confirms high reliability on the integrated model. That yellow color is actual line and blue color is predicted model. It is compared with the regions and yield tons per hectare. So feature importance scores are means how that yield prediction factor is depending on the importance. Means rainfall is important by 25%, NDVI induces 22%, soil moisture indicates 20%, like that, temperature, fertilizer use, and overall insight. Conclusion: integrating agrometrical farm level and inward sensing data greatly improve the crop yield prediction accuracy, and rainfall and NDVI are the strongest predictors. Soil moisture, temperature, and fertilizer have lesser impact. Close match between actual and predicted yields confirms model reliability, supports climate smart agriculture, better input use, and stronger policy planning for food security. This can be extended to other crops, regions, and real-time border precision agriculture applications. These are the references some. Thank you.
Amar sir, any questions?
There might be similar kind of systems exist. Are you comparing to the existing system?
No, means we taken the crop as a paddy rice item. So they have taken for different crops also different regions. So we have taken for rice.
As similar to rice, whether
Uh,
there is another system working for the rice, are you
means
comparing
they
to the same?
no, so they use maybe single sources. We are using multi sources data, sir.
Okay. And what accuracy you are getting then?
That's a 0.89, sir, highest. R square
Okay.
value is 0.89, sir.
What is the significance of R square value in this?
Sir, means it is 1 minus independent variable by dependent variable, sir. It means it is range is 0 to 1. 0 means it is no use, and 1 is it is high ideal case.
For what? What that is indicating?
That indicates the error, means actual yield and predicted yield error rate, sir.
Okay. Okay. Thank you very much.
Okay, okay, sir. Thank you.
Yes, thank you, sir, for your presentation.
Yeah, madam, thank you.
Hello. Hello.
Yes, hello, sir. Please present your study on quantum dot cellular automata based design of comparator circuits.
Am I audible?
Yes, sir.
Is my screen visible?
Yes, sir.
Uh, so, good afternoon, respected chair, honorable judges, and everyone present here. I am Abhishek Kulkarni, and today I will be presenting our research work titled Quantum Dot Cellular Automata Based Design of Comparator Circuits. This work has been carried out along with my co-authors Suhas, Vishwanath, Pratik, Shrish, Saroja, Vijay, and Rajeshwari. In this presentation, I'll walk you through why we choose QCA, how we designed the comparator circuits, and what improvements we achieved compared to existing designs. So I'll begin with the hello. One second, I have an issue.
Please continue next slide.
I'm not able to go into next slide. So one second, yes. So I'll begin with the brief introduction. So our research lies in the area of nanoelectronics and low power digital systems. As we all know, conventional CMOS technology is approaching its physical and power limitations, especially as device dimension shrink further. Because of this, alternative computing paradigms are being actively explored, and QCA is one such promising technology. Unlike CMOS, QCA does not rely on current flow. Instead, it operates based on electron position and Coulombic interaction, which makes it inherently low power and high speed. In this work, we used QCA Designer E simulation tool to design and evaluate QCA based logical circuits. Specifically, we proposed two different 1-bit comparator circuits with a strong focus on optimization in terms of area, power dissipation, and cell count. So the core contribution of this work is twofold. First, we present two logically different QCA-based comparator designs. Second, we apply optimization strategies to significantly reduce cell count, layout area, and power consumption. As shown here, both proposed designs outperform existing QCA comparator circuits, making them more suitable as building blocks for larger nanoscale systems. So now coming to the motivation behind this work, although CMOS technology has dominated digital design for decades, technology scaling has introduced serious challenges such as increased leakage power, heat dissipation, and interconnect complexity. This has created a strong demand for energy efficient and compact alternatives, especially for future computing systems. So QCA offers several advantages. So that is very low power dissipation, high switching speed, high device density. So, however, our literature survey, we observed a clear research gap. Most of the existing QCA comparator designs focus on either area optimization or power optimization, but not both simultaneously. So the motivation of our work was to design compact low power comparator circuits, which are fundamental components in arithmetic and decision making units of digital systems. So moving on to methodology, we begin by designing two different logical expressions for one bit comparator. These logical designs were then carefully mapped into QCA layouts using QCA Designer E. To achieve optimization, we focused on three main aspects: reduction in cell count, power optimization by minimizing the switching transitions, and logical simplification using Boolean minimization techniques. After implementation, we simulated the circuits and validated their correctness. Finally, we compared our proposed designs with existing comparator circuits in terms of area, power dissipation, and cell count. So here you can see the QCA layouts of the circuits we proposed. So special care was taken to reduce unnecessary wire crossings, minimize the number of majority gates, and ensure the stable signal propagation. These designs choices directly contributed to the performance improvements we achieved. So we can see that in the results. So now coming to the most important part, results. This table compares our proposed designs with existing QCA based comparator circuits. From the observation, we can see in the existing comparator circuits, the QCA cells used are 39 and the area used is 42,429 nanometer square. And the power dissipation is 720.9 picowatt. So as I said, we have proposed two comparator circuits. So in the first comparator circuits, the cell counts is reduced to 26. Sorry. So the total cells we used is 26, and the area reduction was up to 37,663.65 nanometer squares, and the power dissipation was reduced to 644.8 picowatt. So in the next second proposed one bit comparator circuit, so the cell count was the same as the first circuit, that is 26 cells, but we can see the significant reduction in the area, that is 23,824.44 nanometer square, which is almost the half. We have reduced the area by half, and the power dissipation was 544.25 picowatt. So so there is a 33% reduction in cell count, 43% reduction in area, and 24.5% lower power dissipation. These improvements clearly indicate that our circuits are more compact, energy efficient, and scalable. Such optimized designs are highly beneficial when integrated into larger arithmetic units or multi-bit systems. So these slides show the simulation waveforms and outputs of both comparator circuits. The simulation results confirm the correct functionality of the design and validate the reduced switching activity, which is primary reason for lower power dissipation. So to conclude, in this work, we successfully designed and optimized one-bit comparator circuits using quantum dot cellular automata technology. The proposed design shows significant improvement over existing works, particularly in terms of cell count, area, and power dissipation. Our contribution provides efficient building blocks for scalable and low power nano computing systems, and further strengthens the case for QC as a potential alternative for CMOS in future technology. Thank you, sir. So I'll open the floor for questions.
So good work. So what's the accuracy you are getting and what are the performance parameters you are keeping?
So in the digital VLSI circuits, the power performance metrics are area, power dissipation, and delay, sir. So as I have shown in the result section, we have reduced the area up to half, sir. So from 42,429 to 23,824, and power dissipation is also reduced from 720 picowatt to 544.25 picowatt. So these are the both performance metrics we used. So QCA cells are reduced from 39 to 26. So only 26 cells are used in our circuit, sir. So coming to delay, so there is no delay in QCA. So that is the main advantage of QCA over CMOS. So the existing one bit comparator circuit also comes with a zero delay, and our circuit will also come with a zero delay, sir.
Okay. Thank you very much.
Thank you, sir.
Yes, thank you, sir, for your presentation.
Thank you, ma'am. Thank you.
Now, next, I would ask Vani Patel to present a study on satellite imagery analysis for mining detection using CNN-based segmentation approaches.
Yes, ma'am. Ma'am, is my screen visible?
Yes, ma'am. Please start with the presentation.
Okay. Good afternoon, everyone. I'm Vani Patel from Charoset. Today, I'll be presenting our work titled Satellite Imagery Analysis for Mining Detection using CNN-based segmentation approaches. This research focuses on the automated detection for unregulated mining activities using deep learning techniques and applied to satellite imagery. Unregulated mining is a critical environmental issue, particularly in forested regions. These activities lead to large-scale deforestation, destruction of natural habitats, and contamination of water bodies due to mining runoff. Traditional monitoring approaches such as manual field surveys and basic satellite image inspection are slow and inefficient. They struggle to scale across large geographical areas and often fail to detect covert mining activities hidden under dense vegetation. Therefore, there is a strong need of automated, accurate, and scalable detection systems. The motivation behind this research comes from the growing environmental and socio-economic damage caused by unregulated mining. Existing monitoring systems lack the capability to detect such activities efficiently and in real time. Deep learning-based image segmentation offers a promising solution by enabling precise region-level detection. Our primary objective is to compare four CNN architectures: ResNet 152, DenseNet 121, EfficientNet B5, and VGG19 to identify the most effective model for mining detection. Previous research demonstrates that CNN combined with remote sensing data are effective for mining detection. High accuracies have been reported using UAV imagery, satellite data, and architectures such as UNet and RetinaNet. However, a key research gap exists. There is limited comparative analysis evaluating multiple CNN backbone architectures on the same segmentation dataset. Our work addresses this gap by performing a systematic comparison under identical experimental conditions. We use the segmentation unregulated mining dataset from RoboFlow Universe. It consists of high-resolution satellite images in JPEG format with YOLO-style polygon annotations. The dataset is divided into training, validation, and test sets. Several challenges are associated with the dataset, including cloud-covered dense vegetation and strong visual similarity between authorized and unregulated mining operations. Additionally, accurate boundary annotation is essential for reliable segmentation. To ensure compatibility with deep learning models, we applied a structured pre-processing pipeline. Images were normalized using ImageNet mean and standard deviation values. Data augmentation techniques such as flipping, rotation, and brightness variation were applied to improve generalization. YOLO polygon annotations were converted into binary segmentation masks, enabling precise region-based detection of mining areas. We evaluated four CNN architectures: ResNet 152, which employs deep residual connections to address vanishing gradient issues. VGG19 uses a classic design with small 3x3 convolution filters. EfficientNet B5 applies compound scaling to balance accuracy and efficiency, and DenseNet 121 introduces dense connections that promote feature reuse and strong gradient flow. All models used for transfer learning with ImageNet pre-training and were trained using multiple optimizers, including ADAM, SGD, and ADAMW. This slide illustrates the complete system workflow. The process begins with data collection and polygon-based labeling of satellite images. Images are then pre-processed and annotations converted into segmentation masks. Multiple CNN architectures were evaluated and trained using transfer learning. Finally, the trained model is deployed to automatically detect and segment unregulated mining regions from satellite imagery. Our experimental result shows that DenseNet 121 achieved the highest accuracy of 75%, ResNet 152 followed with 73%, BGG19 with 72%, and EfficientNet B5 with 70%. DenseNet 121 outperformed the other models due to its dense connectivity, which enhances feature reuse and improves segmentation quality across varied mining patterns. To conclude, this research demonstrates that CNN-based image segmentation is an effective approach for automated detection of unregulated mining activities. Among the evaluated models, DenseNet 121 delivered the best performance on the RoboFlow dataset. Future work will explore multimodal data fusion using satellite imagery and adopt self-supervised learning to reduce labeling requirements and develop real-time edge-based deployment solutions. Thank you. I welcome any questions.
So you are comparing it to other system, right?
Yes.
What's your accuracy you received?
We have evaluated 4 CNN models. From those 4 models, we achieved 75% accuracy from the DenseNet 121 model.
Okay, so accuracy seems to be less actually.
Yes, because due to the data set complexity and real world challenges, such as I mentioned earlier, there are some challenges the model could face, like cloud cover and strong visual similarity between legal and unregulated mining areas in the picture. And so, like the 75% accuracy on after such challenges are, I think, real.
So how will you improve the accuracy in this case?
We could change our dataset, like we could train our model on multiple dataset, as we have trained only on the one dataset, which is RoboFlow universe dataset. And to achieve high accuracy, we can use other multiple datasets also.
Okay. Okay, thank you very much.
Thank you.
Thank you, ma'am, for your presentation.
Thank you.
Now, next, I would call Sushant Kabir Datta for presenting their study on sensor-based human activity recognition using machine learning and deep learning approaches, a comparative study.
Hello. Good afternoon, ma'am.
Good afternoon, sir.
Yeah. Let me share my slides. Can you see?
Yes, sir.
Just tell me, is it visible?
Yes, sir. We can see the table of contents.
Yes. Okay. Well, good afternoon to everyone present here. My name is Sushanta Kabir Datta. I am from Northeastern Hill University, Department of Electronics and Communication Engineering. The title of the manuscript is Sensor-Based Human Activity Recognition Using Machine Learning and Deep Learning Approaches, a Comparative Study. I have a co-author with me, Ms. Shivangi Nanda, but she is not presenting here. So the contents of the presentations are like this: introduction, the related work and research gap, methodology, experimental setup, results and discussion, conclusion and future directions, references. So coming to introduction, human activity recognition is having a very wide range of applications. So some of them are like health monitoring, elderly care, smart homes, security, rehabilitation, human-computer interactions, to name a few. We have broadly 2 types of HAR available. One is vision-based HAR, where cameras are used for capturing images and videos, but that has the risk of privacy. Then we have the sensor-based HAR, which are non-intrusive, lightweight, and more practical for daily usage. For example, we have wearable body-worn sensors like accelerometers, gyroscopes, which are internal in nature, smartphone, smartwatch, etc., which are external. then object sensors like RFID, and ambient sensors like radar, Wi-Fi, temperature sensor, pressure sensor, etc. Now, for hard research, when we had tried to see, we found out that there are many open source databases available. Out of that, UCI, HAR, Opportunity, mHealth, Wisdom, CASAS, Kaito, these are some very popular data sets of open source data sets which are available for research. So we set the objective of our study in this way, that to find a conclusive stance between the machine learning and deep learning approaches for sensor-based HAR, where we will try to perform the matrix analysis, where we need to do first the modeling by using classical machine learning algorithms for HAR sensor data, then to use deep learning frameworks for hard data, and then compare the results and find out the best model. So in essence, we want to answer the question, can deep learning models outperform classical machine learning models in well-engineered sensor dataset? The objective is on well-engineered sensor dataset. Then the related work and research gap. When we came to the related works, a detailed literature review has been presented in the manuscript. So the most important things what we have extracted out here is that it is observed that isolated studies are made on HAR in several datasets using machine learning and deep learning models. However, one research gap we found, that is that no comparison has been done among these models in one particular dataset. Therefore, we have taken up this work using UCI HAR dataset and applied it across different models. We use both baseline and tune models to perform the analysis, and finally we came out with the best performing model after experimentation, which we are going to present here. So coming to the methodology, we have used 4 machine learning algorithms at baseline: random forest with 200 trees, support vector machines with a linear kernel, then neural network, 3 hidden layers, 11 units each, 10 nearest neighbor classifier, which has where we fixed k values at 24. Then we did the hyperparameter tuning for these models using randomized search CV algorithm with 5-fold cross validation. This tuning is computationally efficient and helps us to get the optimum value of the parameters. These parameters like trees, kernel type, regularization, hidden layer, k values, all are optimized for maximum accuracy. So the values are optimized for maximum accuracy. So this produces us with the better results with minimum risk of potential runtime delays. Then coming to the deep learning models, we use 4 deep learning models at baseline. First, the CNN model with 3 convolution layers, 1D convolution layers with 32, 64, and 64 filters each. Then each has a kernel of size 3 and it uses ReLU activation. Finally, we use a dense layer which uses softmax activation for output prediction. So the model can be visualized with the help of a block diagram like this. So 3 convolution layers, each layer followed by max pooling layer, and finally a flattened layer, dense layer for the softmax activation function for output prediction. So this is the CNN model. Then the second baseline is the LSTM model, where we use the LSTM network containing of 2 LSTM layers. First layer has 64 units, second layer has 32 units, and thereafter a flattened layer which leads to the output dense layer. A softmax function is used again for the activation, and the model with the help of block diagram, you can visualize it like this: input, then 2 LSTM layers, flattened layer, dense layer, finally the prediction of the output. Next, we have formulated the model for a GRU, and GRU and LSTM are basically similar structure we have used. So instead of LSTM layers, we have used the GRU. So the model architecture will remain same as in the previous figure, like this. Only LSTMs will be replaced by GRU. Then fourth, we made a hybrid of CNN and LSTM combination, where one 1D convolution layer with 64 units are used. Then one LSTM is used for with 64 units. Then conv 1D, max pooling, and flattened layers are individually wrapped in a time distributed manner. Then batch normalization is used. Then finally, we use a softmax function in the dense layer for recognition of the activity. So the block diagram for this is like this. Then experimental setup. So we use the model parameter setups, the optimizer, loss function, and other metric parameters for training in all the other models by standard compile method. We selected Adam W optimizer for minimizing categorical entropy loss. The hyperparameter tuning for the deep models are done by using Bayesian optimization tuner. It used 10 trials for each case. Each trial has 45 epochs for CNN and CNN LSTM and 20 epochs for LSTM and GRE. 20% validation split is maintained across all models, across all the models. Now coming to the database, so we have selected the UCI HAR database, University of California Irvine Human Activity Recognition dataset. So this is a publicly available dataset, can be found out from UCI Machine Learning repository. So it contains 30 participants performing 6 activities: walking, walking upstairs, walking downstairs, sitting, standing, and laying. So participants are logged with smartphone on their wrists, and based on this data, the experiments are carried out. So triaxial linear acceleration and triaxial angular velocity is recorded at 50 Hz. Smartphone's accelerometer and gyroscope sensors are used. Acceleration is broken down to body acceleration and gravity, and therefore 9 raw features were produced. The data cleaning and pre-processing are done by noise filters, sampling with fixed windows at 2.56 seconds and 50% overlap. And train test ratio is maintained at 70:30. Actual training data is 7,352, while testing data is 2,947. Then from the ML models, the best performing model we found out as the SDL. So it produced an accuracy of 96.54% after tuning has been done. The confusion matrix we found out is shown in this figure. So the clarity will come when we look at the observations that are listed like this. So from the confusion matrix, activity 6, that is laying, is most accurately recognized. So you can see that the activity 6 is the laying, the activity laying, which has been recognized completely correctly, fully correct manner. Then activity 5, standing and sitting, were confused several times. And then again, activity 2 and 3, working upstairs and downstairs, are also confused with each other and with activity 1, which is linear working, for a large number of times. So this is the results of the machine learning models, the best performing model SDL. Then coming to deep learning models, among the deep learning models, LSTM is found out to be the best performing model. It is measured by observing the validation loss and accuracy curves. So these are shown in the actual manuscript. So from there, we have found out that LSTM stood out as the best performing model. So after tuning, the accuracy of LSTM is found out to be 93.62%. And the second best model is found as CNN, who is produced.
Sorry for interruption, sir, but you have crossed 9 minutes of your presentation.
The best performing model is 92.16%. Confusion matrix for LSTM is shown here. So here, the observations, the results and findings are like this. The SDM remained as the most standout model among all the models with a recognition accuracy of 96.54%. This is because the higher dimensional feature mapping through competent kernel functions, which increases the rate of correct recognition. It is also found that the fine-tuning of hyperparameters refine the effectiveness of the models. So we found it for CNN LSTM as the model accuracy increases by 2.38%. Second, GRU and LSTM model accuracy is increased by 2% because of hyperparameter tuning. So this happens because that it reduces the effect of overfitting. So in brief, when we use deep learning models to work with less relevant features, then what may happen is that they may sometimes perform poorly than as compared to our classical machine learning algorithms. So this is shown with the help of this bar diagram. where we see that the SVM has the highest accuracy, and in among the DL models, LSTM has the highest accuracy, but SVM supersedes LSTM in the well-engineered data. So the conclusion and future directions are like this. So after close examination, we have found out a conclusive stance that between the activities sitting and standing, they are most confused among all the models. This is because we have ascertained the reasons, because these two postures generate very similar inertial structures. So distinguishing them from one another requires contextual informations like the posture angles or body orientation. And activity laying is found to be well recognized across all the models. Hyperparameter tuning obviously increases the performance of the deep learning models. In accuracy comparison, SVM outperforms all the deep learning models. The reason behind is that while deep learning works excellently with the raw large-scale data, in case of well-engineered small-scale data set, sometimes the deep learning may not perform well as compared to classical machine learning algorithm. So
Sir, due to time constraint, I please request you to conclude your
this is the last slide now. So overall study shows that classical machine learning, especially SVM, can outperform deep learning for a sensor-based dataset when it is well-engineered dataset. As a part of future study, we can use the raw datasets and try to see how the deep learning model might supersede the machine learning algorithm. So that's all from the presentation side. Then the selected references, these are also listed in the main paper. And finally, thank you very much for giving me the opportunity to present here in this conference.
Okay.
Thank you.
Good work. Good.
Yes, sir.
Good work. Thank you very much.
Thank you so much, sir.
Yes. Go ahead.
Yes, thank you, sir, for your presentation.
Well, ma'am.
Now, next, I would like to call Pradyumna Ramgirwar to present a study on 10 Gbps ROF transmission model at 60 GHz using NRZ for 5G networks.
Yes, ma'am. So here it's visible now. So the title of the paper is 10 GB per second, 60 gigahertz radio or fiber transmission line. So as the name suggests, we have to transmit this much amount of data to various distance using 60 gigahertz, and we will see how this will work. So 5G network uses waves and the bandwidth between 30 gigahertz to 300 gigahertz, and we are using specially at 60 gigahertz. And these wave have high path loss and limited range. High path loss means we have much more attenuation, but we require some gain. So gain is the positive power and attenuation is the negative power. To overcome this scenario, we have used the RF solutions. With the help of RF, we can efficiently transmit high frequency data to a long distance using fiber optics. So it combines a high bandwidth of optical fibers using wireless connectivity. Applications is ideally it is used in highly densely populated urban areas. So our focus is on transmission of high speed 10 GB per data, 60 gigahertz using fiber optics. Then the objective is to evaluate performance of this system using OptiSystem software. Specific goal is we have to specific goal is we have to compare using different channels like one channel, two channel, four channel, or eight channel with different kilometers, and measurement factor is called quality factor, beat rate, and I diagram. So parameters we have used is 10 GB per second data, carrier frequency 60 gigahertz, non-returning to zero modulation, and tool is OptiSystem. What happens we have used the return to zero. If it is written to zero, then we may lost our data. That's why I prefer to use the non-returning to data modulator. So this is the main block diagram, and this one is the transmission side, this is the carrier side, and this is the receiver side.
And then we have in the transmission side we have 10 GB per second data with the NRZ, continuous wave laser lights, as the carrier frequency. Then we have Mach Zehnder modulator and lithium niobate modulator. Mach Zehnder modulator is used to modulate the data, and lithium niobate modulator is used to modulates the data carrying optical signals. Then we have transmission channel is the fiber optics. Then amplification is the optical fiber for dispersion management. See, it is the it means basically it's the light travel with the information. So dispersion is must happen there. So we have to control that dispersion. So we have used the optical fibers. Then at receiver end, we have Gaussian filter, photodiode, beta rate, and eye diagram analyzer. So our end goal is to receive the original baseband signal, that is 10 GB per second, 60 gigahertz, in the form of original, that is baseband signal. It's our end goal. So this is the diagram for one channel system at 30 kilometer. It is more sharp as compared to this one, because this is at 60 kilometer. The previous one is at 30 kilometer at the one channel system only. So key finding for the both of these diagrams: one channel system is best overall performance across all the distances. Low range between 0 to 5 kilometer, we have 0 bit error rate. Medium range between 10 to 15 kilometer, performance is good, but yeah, it's acceptable. For the 70 plus kilometer, at 74 kilometer, our system is failure, because system will give bit error rate as one. So it's good up to 74 kilometer. Beyond that, we have to increase the number of channels that we will see in the next slides. This is 4 channel system at 40 kilometer. This is 4 channel system at 60 kilometer. Then the general trade is, as we increases the number of channels, we can also increase the capacity, but eventually quantity increases and quality decreases. That's why output signal contains more noise and it reduces signal efficiency. 2 channel system is stable up to 50-60 kilometer. Beyond that, efficiency will slightly decrease. 4 channel system will for 4 channel system, quality factor deteriorate as we increase the distance, but it is up to 30 kilometer. It's good. For 8 channel system, degradation was faster than the 2 channel 4 channel system, because as we increases the quantity, quality is also decreases. And acceptable quality factor is somewhat uh, quality factor is 4 at 50 kilometers. So the conclusion is, if we don't have the channel constraint or data constraints, so we can use the 1 channel 2 channel system as compared to 4 channel system. So here you can see the first diagram is maximum quality factor for different channels. Then the second diagram is bit error rate for the different channels for all of 4 categories of channels. Then the first diagram shows 1 channel system is best. For multi-channel system, the quality factor decreases from 5 to 3. Then minimum bit error rate remains 0 for all the channels up to 50-60 kilometer. For, as I said earlier, for 1 channel system will it fails at 74 kilometer. Multi-channel system will fail slightly later than the 1 channel system, near about 100 kilometer. But the bit error rate of multi-channel system will slightly increase from 50 to 90. So another result is that quality factor and I height decreases while the bit error rate increases. Means they both are inversely proportional to each other. So the key conclusion is, if we don't have a channel constraint, or if we don't have to hurry, we can use the 1 channel system. Or then the uh, multi-channel system is good between 30 to 50 kilometers. As the distance increases, quality also decreases. Then data transmission beyond a significant distance is unacceptable, as the quality factor decreases, bit error rate increases, and eye height of the final diagram is also increases. When recommendation is same, use the 1 channel or 2 channel system. Then we have future scope. As I said earlier, optical amplifiers gives the fiber optic dispersion. So we can ignore this dispersion when we use the orthogonal frequency division multiplexing, OFDM. And then we can use the other modulation technique also, like QAM, PAM, PPM, or PCM also. And advanced techniques use also, like forward error corrections and optical fibers, to extend the limit and
to transmit the efficiently data, and we can increase the gain by using this technique. So yeah, thank you.
So, what performance parameters you were used for your analysis?
Performance parameter is quality factor, beat error rate, and eye diagram. Here is the performance factor. Yeah. This is the
So,
quality factor, beat error rate, and eye diagram. This is the performance factor. With the
what
help of
accuracy you are getting through this?
for one channel system, it's best up to 74 kilometer, and for multi-channel system, it is good, or we can use the multi-channel system up to 30 to 50 kilometer. But
Are you
for
comparing with the existing system?
sorry.
Are you comparing this with the existing system?
Yes, the difference between that existing system is more secure than this system, because in the existing system we are using like pulse code modulation or pulse duration modulation, and to control that pulse, it's more hard. So yeah,
Mhm.
existing system is more secure than this system.
Okay, so how the security you can achieve through this then?
See, here we have, if we have used the PCM or PDM, then the security is also increased, because the in pulse amplitude modulation, the data or information is stored in the pulse, in the amplitude of the pulse, but in the code modulation or duration modulation, the data is stored in the time gap of that system, and so it's hard to crack the timing of the pulse. So if we use the PCM or PDM, we can achieve the security.
Mm-hmm.
Yes, sir.
Okay. Thank you very much.
Yes, sir. Welcome.
Yes, thank you, sir.
Yes, sir, ma'am.
Now, lastly, I would like to call Nida Iftekhar to present her paper with paper ID 1061.
Yes, ma'am. Am I audible?
Yes, ma'am.
Okay. Just a second.
Pradyumna sir, can you please stop your screen share? Thank you.
Just a second, ma'am. Are my slides visible?
Yes, ma'am.
Okay. Good afternoon, everyone. Myself, Nida Iftekhar. I'm going to present my paper, a review of machine learning algorithms for respiratory disease diagnosis. Currently, I'm working as assistant professor in Jamia Hamdard. So I'll be going through the problem statement, the objectives. I have considered several researches that have been done in this domain, and I've identified certain research gaps that exist. And based upon those, I have proposed my methodology and my research plan. So as we know, machine learning is a part of AI, where computers use statistical methods for self-learning without being explicitly programs. So it plays a great role when it is used in the domain of biomedical. So for this analysis, I'm going to use a data set from multiple healthcare providers, and for the diagnosis of respiratory diseases such as pneumonia, asthma, COVID-19, lung cancer, and so on. So in order to examine the most dominant features of diagnosis and prediction of these diseases, we'll analyze a data set that will describe different values about the demographic profile, medical measurements, habits, and associated symptoms, and finally the dependent variables, if there are. So I will also be considering the pulmonary measurements coming from the spirometer, which is a device that estimates the volume of air inhaled and exhaled by time. So particularly, it will be my approach will be focusing on two main applications: the diagnosis of respiratory diseases, prediction of mortality risk, severity, and life expectancy of the patients. So, talking about the researches that have been done in this domain, Demetris Pathis et al. So they have considered a data set of 132 patients from Greece, and they have presented the descriptive statistics of each variable and established correlations between the dependent and independent variables using logistic regression. Then Mathia et al. So they have taken a study, they have taken into consideration 554 adults consisting of 42% males, in which 38% were previous or current smokers. So they applied logistic regression models were fitted, selecting features by means of logit boost algorithm. Then another study in which they have taken the pulse oximetry data corresponding to 11 asthma subjects who breathe at the range of controlled respiratory rates. So now in this case, the proposed technique is unit and LSTM algorithms to this data. And in this approach, they have achieved for all p-values less than equal to 0.001. Then Kevin et al. They have taken a asthma data set that is publicly available in mHealth dataset, and again they have applied well-known supervised algorithm. And in this, they have achieved area under ROC curve greater than 0.87 by applying logistic regression and naive-Bayes classifier. Another research in which David et al. So they have taken data from UCLA Health Systems in Los Angeles, California. Now they have applied an ensemble model in which was created based upon individually trained machine learning models. Uh, in this case also, they have achieved a sensitivity of 0.93 and specificity of 0.64. Then M. Cooker et al. They have taken routine blood test of 5,333 patients with various bacterial and viral infections, and they have evaluated the models using repeated stratified tenfold cross validation. Then again, their model have achieved high sensitivity of 81.9% and a specificity of 97.9% and area under ROC curve of 0.97. Another study in which Hoyt Burkle et al. They have considered 197 patients who enrolled in the Ready clinical trial that were visiting the emergency department in a hospital. It was done in the COVID scenario between March 24, 2020 to May 4, 2020. Now they have achieved a high sensitivity of 0.90, then MEWS that is 0.08. Another study in which they have considered a data of 2,364 patients, and they have basically analyzed what are the effects of the medicines remdesivir and corticosteroid who are treated with these medicines. They have applied gradient boosted decision tree models for predicting treatment benefit, and in this case, they they found out that corticosteroids and remdesivir was significantly associated with an increase in survival time with a hazard ratio of 0.56 and 0.40 respectively. Another study which has been done on Koswara and Sarko's dataset, which is publicly available. Again, they have analyzed this data, which was for particularly COVID-19 patients, and they have achieved an AUC of 0.98. Then another study in which the data set that has been considered as online database that is available from National Center for Biotechnology Information and Gene Ontology database. Again, they have considered chest X-ray images and they have applied deep CNN model. So they have improved the classification accuracy from 82.14 to 92.86, and their sensitivity and specificity are 90.91 and 94.12% respectively. So in all the approaches that have been considered, so problem that I have identified is that the data set should be fetched from various healthcare industries rather than just focusing on a data or identified from just one source. It should be obtained from multiple sources. Then application of visualization techniques followed by machine learning techniques. And the data should be from authenticated sources. It should be a primary data instead of the data set that is available online. and the data set should be large enough so as to develop a more efficient model for the diagnosis of respiratory diseases that will be more helpful for the medical fraternity. The developed models should be adaptable to learn itself and provide a better research solution. So, my objective is developing a system for detection and diagnosis of pneumonia, COVID-19, and asthma, having a variety of attributes to describe each entity of dataset really. Then improving the performance of these models by increasing the size of the data set at lower breathing rates. Then developing early warning algorithms for identification of diseases based upon the existing attributes of the patients. Then calculating the life expectancy of the patients using the CT scan and lung X-ray reports of the patients. Then developing a machine learning model for COVID-19 and other diseases diagnosis based upon the data collected from multiple healthcare sources rather than considering just one or two sources. So currently, I have taken the Harvard Dataverse. The size of this data set is 2.4 GB. It is comprising of chest X-ray images corresponding to lung patients, and I have already applied Nutrect hybrid convolutional neural network model, and particularly this is classifying chest X-ray images based upon fully collected layers. I am able to identify uh, the patients for pneumonia diagnosis. Uh, and in future, I will be working on multi-class classification. Currently, I have identified the pneumonia patients, but in future, I will be working upon multiple diseases classification. As we can see here, the input is a test and training set from the Harvard Dataverse currently that I have worked, then training this model with fully connected layers, then storing the highest test accuracy, which is achieved at the corresponding epoch, then extracting features using weights, then training ML classifiers using random forest and decision tree.
Ma'am, gentle reminder that you've crossed 9 minutes.
Okay. So the model with the highest test accuracy will be selected, and predictions will be made based upon the model that performs best. The output is detection of the pneumonia cases. So, developing a systematic approach for multi-class respiratory disease detection from chest X-ray images, and I'll be also considering the CT scans of patients. Uh, these are the references that I've taken into consideration.
What's the accuracy you are getting through?
Sorry, sir.
Accuracy.
Sir, I have achieved accuracy of 91%. I'm working on it to improve the accuracy. That's why I have not presented my results over here.
Okay. While be getting this accuracy 90%, what is the reason? How you can improve it?
Sir, I will be working on layers of the CNN that I have applied. Currently, I have just applied a CNN model, and I will be making certain modifications in the layers so that the results will improve.
Okay. Okay. Thank you very much.
Thank you, sir.
Yes, thank you, ma'am, for your presentation.
Thank you so much, ma'am.
Now, all the presentations are hence done, and we will be proceeding with the closing remarks. I
Ma'am?
sincerely thank. Yes, ma'am. Do you have any question, ma'am? All right. Yes, ma'am.
Yes, ma'am. It was scheduled offline, and I shifted to online one. So thank you so much for considering my request.
Yes. Thank you, ma'am. Thank you.
Okay, ma'am.
So, proceeding, I sincerely thank our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 10th version and all the previous 9 versions of the conference. We will be happy to have you in the 11th version in 2026. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Hence, I would request everyone to kindly cooperate with the team of ICTCS 2025. I would also like to thank our session chair, Professor Amar Buchade sir, for chairing the session. I'm sharing a token of appreciation on behalf of Team ICTCS and Global Knowledge Research Foundation and partners. Thank you for your presence, sir, and please share any
Thank you
closing
very
remarks.
much. Thank you. So all were the good papers. So I am requesting all the authors to include whatever the feedback you have received in the paper. Thank you very much.
Yes, thank you very much, sir. Now, before we conclude, I would request everyone to please turn on your cameras for a quick snapshot. Yes, thank you, everyone. Have a great day ahead. Stay safe. Thank you.
Thank you very much.
Yes, thank you, sir.